Welcome back to INST 314, Statistics for Information Science. I'm your host, Shawn Janzen. We're continuing our talk on Inference Part 3, and in this case, our topic 7.6 is going to carry us into the theoretical land of the sampling distribution. I promise I'll try not to make this too painful now that we're back in theory land, and we'll get ourselves through it. So again, we're going to talk about framing within the sampling distribution. We're going to move later into the central limit theorem and kind of wrap things up a little bit more. So let's start talking about that sampling distribution. Keep in mind, we're going to recall the data analytics workflow that we talked about early on in this course. You start by identifying the research question and defining the population. This is the who and what we're studying and who we're going to be able to make conclusions about. You go ahead and take a sample, which is hopefully going to be representative, and which means we're going to accurately represent the population. We're going to use this data to make conclusions, and we're going to say things like, are these groups significantly different? Can we trust the trends that we see in the population? Are these relationships here? We're going to evaluate then, lastly, your conclusions. How confident are you? What is your error of margin that you could be wrong? Error of margin refers back to those things like the confidence intervals. So far, we've gone ahead and looked over the question part, and we've talked about the population part. We've talked about getting samples, and we've talked about describing and visualizing those samples. But now we need to go dig in a little bit deeper about the making conclusions part. So let's go ahead and take a look at a particular example here. A UMD graduate student, Capstone, has developed a new email add-on feature to help users of UMD Google Email recognize if an email might be spoofing for phishing. They created an experiment to test if the new interface against the current UMD email interface. They assign 100 volunteer participants into two groups of 50 at random, a control group that keeps the current interface, and a treatment group that has the email add-on feature. First, let's ask ourselves, what is the population, the sample, the unit of observation, and what is our primary research question? Go ahead, stop for a moment and think. I'll wait. Okay, let's keep going. So, after we go ahead and look at this, we would say that our population is the graduate student body at University of Maryland. Actually, it would be the University of Maryland students broadly, since it would be everybody's using the Google email interface. The sample would be the 100 volunteer participants. The unit of observation would be University of Maryland students, since they are the lowest common denominator that we're looking at. And the primary research question is, does this particular email add-on feature allow us to recognize if emails might be spoofed for phishing or not? So after we go ahead and run their experiment, we look at the results. The team is going to show that they correctly identified about 46% of them in the treatment group. So 46 people in the treatment group, the email add-on feature found the email that was trying to do spoofing and phishing. And in the control group, those that did not have the add-on, we only found the spoofed emails about 30% of the time. So can we conclude that the email add-on was successfully increasing the identification of the spoof phishing emails? The percentages look like it says that they do, but that's just from our sample. We want to go ahead and try and do an inference to our larger population. We need to see, are these differences large enough? So was it due to random chance alone as well? Could we have just had a sample of 100 volunteer participants, and even though we did random assignment, is it a difference that is different enough? So let's talk about some point problems. Population parameters, again, I've said again and again, are unknown. The sample statistics can give us a point estimate. We can get means and proportions from them. And so we're going to try and get those means and proportions as close to the population parameters as we can, but we never know how close we are since the population parameter remains unknown. Think of it this way. Statistical inference is making conclusions about the population parameter, and we want to have some sort of degree of reliability about the statistics that we're producing. So you might have darts and you might be throwing them out into 3 different bullet points. And what you might end up having is that you can have bullet points that are all over the place where you are relatively accurate in your estimations, but you're not precise. If you do this over and over and over again, you're going to get estimates that are in the general ballpark, but you're still kind of far from your center target. You could have a situation where you do samples over and over and over again, and your results are indeed really close to each other. You think you might be right, but when you put it onto the target, you found that your clustering is off the mark of center. And hopefully where we want to be is both accurate and precise, where if we did these tests over and over again, we are tightening around a particular position, and that position happens to be close to the center. So when we're thinking about statistical tests, there's a few different ways to do this. Well, everything we're doing in this course is what we call a frequentist approach, or using frequentist inference. There's a whole other family of statistical thinking called Bayesian Inference that you can teach in another particular class, or learn in another particular class. And that takes into these ideas of what do we know beforehand that helps us figure out about the things that we're trying to predict now, or will be predicting. So when we're talking about the frequentist inferential framework, we're saying that in general we start with assumption that there's no difference, no change, no relation. That's our null. And we are trying to reject that null. We're trying to disprove it. And we use a sampling distribution to help us get us there. So what we say then is we have only one observation in our sample. That's only one plot in a potential distribution of possible samples that we could get. So think about it this way. If we did the UMD grad student email add-on and we did the same experiment 30 times, we would get a slightly different result in the values for the treatment and control groups every time. 30 different trial experiments is going to create a sampling distribution of 30 possible outcomes that we're going to get in each one. So what I might do here is I might simulate out the email add-on experiment with an n of 30, where we have 30 different email experiments that we did. And in each one of these, I could say, what is the proportion of the treatment group that correctly identified their spoofed email? And so this would be a histogram of all of the different times. Some of them were as low as around 0.2, and some of them were as high as 0.6. So some of them found a lot, some of them found fewer, but they started to form a distribution of their own. Now, when we're talking about the sampling distribution here, note, we're only going to observe one value from the distribution at the time. That value is going to come from the sample that we collected. And we can use this theoretical sampling distribution to help us figure out our margin of error. Now, we're talking about the sampling distribution. Where does it fit inside the distributions we're normally talking about? Well, we said that there's a population distribution. This is the population distribution that we don't normally see because we don't have population level data, but there is some average and there's a curve that goes with that average. We just never see it. And then there's a sample distribution. That's the stuff we go ahead and collect. And so we find like a mean and we get a standard deviation of all the observation points that we have. But sandwiched in between is the sampling distribution. And that's where we have a collection of different means. And if we take a distribution of all the different means across all the samples, that becomes the sampling distribution. And that has important implications. So some properties of the sampling distribution is that it's normal in shape. It has a mean equal to the population mean. The more observations you have in your sampling distribution, the closer your mean is going to become to the population mean. And it has a standard deviation that we're going to call the standard error equal to the population standard deviation divided by the square root of n. Remember, when in a sample we do standard deviation divided by the square root of n minus 1 to be more conservative. But when we get into the sampling distribution approximates the population distribution, which is why it is so important and why we can go ahead and use this for all of our inferences. Which brings us to the central limit theorem. And that's going to help us tie the sampling distribution to the population and the sample. CLT, or the central limit theorem, is one of our most important theorems. And I'm going to talk about that in the next video.